Neural networks are good for learning lots of different types of patterns. To give an example of how this would work, imagine you had a 4-pixel camera. So not 4 megapixels, but just 4 pixels. And it was only black and white. And you wanted to go around and take pictures of things and determine automatically then whether these pictures were of a solid all white or all dark image, a vertical line, or a diagonal line, or a horizontal line. This is tricky because you can't do this with simple rules about the brightness of the pixels. Both of these are horizontal lines, but if you tried to make a rule about which pixel was bright and which was dark, you wouldn't be able to do it. So to do this with the neural network, you start by taking all of your inputs, in this case our 4 pixels, and you break them out into input neurons. And you assign a number to each of these depending on the brightness or darkness of the pixel. +1 is all the way white, -1 is all the way black, and then gray is 0, right in the middle. So these values, once you have them broken out and listed like this on the input neurons, it's also called the input vector or array. It's just a list of numbers that represents your inputs right now. It's a useful notion to think about the receptive field of a neuron. All this means is what set of inputs makes the value of this neuron as high as it can possibly be. For input neurons, this is pretty easy. Each one is associated with just 1 pixel, and when that pixel is all the way white, the value of that input neuron is as high as it can go. The black and white checkered areas show pixels that an input neuron doesn't care about. If they're all the way white or all the way black, it still doesn't affect the value of that input neuron at all. Now, to build a neural network, we create a neuron. The first thing this does is it adds up all of the values of the input neurons. So in this case, if we add up all of those values, we get a 0.5. Now to complicate things just a little bit, each of the connections are weighted, meaning they're multiplied by a number. That number can be 1 or -1 or anything in between. So for instance, if something has a weight of -1, it's multiplied and you get the negative of it, and that's added in. If something has a weight of 0, then it's effectively ignored. So here's what those weighted connections might look like. And you'll notice that after the values of the input neurons are weighted and added, the final value is completely different. Graphically, it's convenient to represent these weights as white links being positive weights, black links being negative weights, and the thickness of the line is roughly proportional to the magnitude of the weight. Then, after you add the weighted input neurons, they get squashed. And I'll show you what that means. You have a sigmoid squashing function. Sigmoid just means S-shaped. And what this does is you put a value in, let's say 0.5, and you run a vertical line up to your sigmoid and then a horizontal line over from where it crosses. And then where that hits the y-axis, that's the output of your function. So in this case, slightly less than 0.5. It's pretty close. As your input number gets larger, your output number also gets larger but more slowly. And eventually, no matter how big the number you put in, the answer is always less than 1. Similarly, when you go negative, the answer is always greater than -1. So this ensures that that neuron's value never gets outside of the range of +1 to -1, which is helpful for keeping the computations in the neural network bounded and stable. So after you sum the weighted values of the neurons and squash the result, you get the output. In this case, 0.746, that is a neuron. So we can collapse all that down, and this is a neuron that does a weighted sum and squash the result. And now instead of just one of those, assume you have a whole bunch. There are 4 shown here, but there could be 400 or 4 million. Now to keep our picture clear, we'll assume for now that the weights are either +1, white lines, -1, black lines, or 0, in which case they're missing entirely. But in actuality, all of these neurons that we created are each attached to all of the input neurons. And they all have some weight between -1 and +1. When we create this first layer of our neural network, the receptive fields get more complex. For instance, here, each of those end up combining 2 of our input neurons. And so the value, the receptive field, the pixel values that make that first layer neuron as large as it can possibly be, look now like pairs of pixels, either all white or a mixture of white and black, depending on the weights. So for instance, this neuron here is attached to this input pixel, which is upper left, and this input pixel, which is lower left, and both of those weights are positive. So it combines the 2 of those, and that's its receptive field, the receptive field of this one plus the receptive field of this one. However, if we look at this neuron, it combines this pixel, upper right, and this pixel, lower right. It has a weight of -1 for the lower right pixel, so that means it's most active when this pixel is black. So here is its receptive field. Now, because we were careful of how we created that first layer, its values look a lot like input values. And we can turn right around and create another layer on top of it the exact same way, with the output of one layer being the input to the next layer. And we can repeat this 3 times or 7 times or 700 times for additional layers. Each time, the receptive fields get even more complex. So you can see here, using the same logic, now they cover all of the pixels and more special arrangement of which are black and which are white. We can create another layer. Again, all of these neurons in one layer are connected to all of the neurons in the previous layer. But we're assuming here that most of those weights are 0 and not shown. It's not generally the case. So just to mix things up, we'll create a new layer, but if you notice our squashing function isn't there anymore. We have something new called a rectified linear unit. This is another popular neuron type. So you do your weighted sum of all your inputs, and instead of squashing, you do rectified linear units, you rectify it. So if it is negative, you make the value 0. If it's positive, you keep the value. This is obviously very easy to compute, and it turns out to have very nice stability properties for neural networks as well in practice. So after we do this, because some of our weights are positive and some are negative, connecting to those rectified linear units, we get receptive fields and their opposites. If you look at the patterns there. And then finally, when we've created as many layers with as many neurons as we want, we create an output layer. Here, we have 4 outputs that we're interested in. Is the image solid, vertical, diagonal, or horizontal? So to walk through an example here of how this would work, let's say we start with this input image shown on the left. Dark pixels on top, white on the bottom. As we propagate that to our input layer, this is what those values would look like. The top pixels, the bottom pixels. As we move that to our first layer, we can see the combination of a dark pixel and a light pixel summed together get us 0, gray. Whereas down here we have the combination of a dark pixel plus a light pixel with a negative weight. So that gets us a value of -1 there, which makes sense because if we look at the receptive field here, upper left pixel white, lower left pixel black, it's the exact opposite of the input that we're getting. And so we would expect its value to be as low as possible, -1. As we move to the next layer, we see the same types of things, combining zeros to get zeros, combining a negative and a negative with a negative weight, which makes a positive, to get a 0. And here we have combining 2 negatives to get a negative. So again, you'll notice the receptive field of this is exactly the inverse of our input. So it makes sense that its weight would be negative, or its value would be negative. And we move to the next layer. All of these, of course, these zeros propagate forward. Here, this is a negative, has a negative value, and it has a positive weight. So it just moves straight forward. Because we have a rectified linear unit, negative values become 0. So now it is 0 again too, but this one gets rectified and becomes positive. Negative times the negative is positive. And so when we finally get to the output, we can see they're all 0 except for this horizontal, which is positive, and that's the answer. Our neural network said this is an image of a horizontal line. Now, neural networks usually aren't that good, not that clean. So there's a notion of, with an input, what is truth? In this case, the truth is this has a 0 for all of these values, but a 1 for horizontal. It's not solid, it's not vertical, it's not diagonal. Yes, it is horizontal. An arbitrary neural network will give answers that are not exactly truth. They might be off by a little or a lot. And then the error is the magnitude of the difference between the truth and the answer given. And you can add all these up to get the total error for the neural network. So the whole idea with learning and training is to adjust the weights to make the error as low as possible. So the way this is done is we put an image in, we calculate the error at the end, then we look for how to adjust those weights higher or lower to either make that error go up or down. And we of course adjust the weights in the way, then make the error go down. Now the problem with doing this is each time we go back and calculate the error, we have to multiply all of those weights by all of the neuron values at each layer, and we have to do that again and again once for each weight. This takes forever in computing terms, on a computing scale, and so it's not a practical way to train a big neural network. you can imagine instead of just rolling down to the bottom of a simple valley, we have a very high dimensional valley and we have to find our way down. And because there are so many dimensions, one for each of these weights, that the computation just becomes prohibitively expensive. Luckily, there was an insight that lets us do this in a very reasonable time. And that's that if we're careful about how we design our neural network, we can calculate the slope directly, the gradient. We can figure out the direction that we need to adjust the weight without going all the way back through our neural network and recalculating. So just to review, the slope that we're talking about is when we make a change in weight, the error will change a little bit, and that relation of the change in weight to the change in error is the slope. Mathematically, there are several ways to write this. We'll favor the one on the bottom. It's technically most correct. We'll call it DEDW for shorthand. Every time you see it, just think the change in error when I change a weight, or the change in the thing on the top when I change the thing on the bottom. This does get into a little bit of calculus. We do take derivatives. That's how we calculate slope. If it's new to you, I strongly recommend a good semester of calculus just because the concepts are so universal. And a lot of them have very nice physical interpretations, which I find very appealing. But don't worry. Otherwise, just gloss over this and pay attention to the rest, and you'll get a general sense for how this works. So in this case, if we change the weight by +1, the error changes by -2, which gives us a slope of -2. That tells us the direction that we should adjust our weight and how much we should adjust it to bring the error down. Now to do this, you have to know what your error function is. So assume we had an error function that was the square of the weight, and you can see that our weight is right at -1. So the first thing we do is we take the derivative, change in error, divided by change in weight, DEDW. The derivative of weight squared is 2 times the weight. And so we plug in our weight of -1, and we get a slope, DEDW, of -2. Now the other trick that lets us do this with deep neural networks is chaining. And to show you how this works, imagine a very simple trivial neural network with just one hidden layer, one input layer, one output layer, and one weight connecting each of them. So it's obvious to see that the value y is just the value x times the weight connecting them, w1. So if we change w1 a little bit, we just take the derivative of y with respect to w1, and we get x. The slope is x. If I change w1 by a little bit, then y will change by x times the size of that adjustment. Similarly, for the next step, we can see that e is just the value y times the weight w2. And so when we calculate dE dy, it's just w2. Because this network is so simple, we can calculate from one end to the other. X times w1 times w2 is the error e. And so if we want to calculate how much will the error change if I change w1, we just take the derivative of that with respect to w1 and get x times w2. So this illustrates, you can see here now, that what we just calculated is actually the product of our first derivative that we took, the dy dw1, times the derivative for the next step, dE dy, multiplied together. This is chaining. You can calculate the slope of each tiny step and then multiply all of those together to get the slope of the full chain, derivative of the full chain. So in a deeper neural network, what this would look like is if I want to know how much the error will change if I adjust a weight that's deep in the network, I just calculate the derivative of each tiny little step all the way back to the weight that I'm trying to calculate, and then multiply them all together. This computationally is many, many times cheaper than what we had to do before of recalculating the error for the whole neural network for every weight. Now, in the neural network that we've created, there are several types of backpropagation we have to do. There are several operations we have to do. For each one of those, we have to be able to calculate the slope. So for the first one is just a weighted connection between two neurons, A and B. So let's assume we know the change in error with respect to B. We want to know the change in error with respect to A. To get there, we need to know dB dA. So to get that, we just write the relationship between B and A, take the derivative of B with respect to A, we get the weight, W, and now we know how to make that step. We know how to do that little nugget of backpropagation. Another element that we've seen is sums. All of our neurons sum up a lot of inputs. To take this backpropagation step, we do the same thing. We write our expression, and then we take the derivative of our endpoint, z, with respect to our step that we're propagating to, a, and dz dA in this case is just 1. Which makes sense. If we have a sum of a whole bunch of elements, we increase one of those elements by 1, we expect the sum to increase by 1. That's the definition of a slope of 1. One-to-one relation there. Another element that we have that we need to be able to backpropagate is the sigmoid function. So this one's a little bit more interesting mathematically. We'll just write it shorthand like this, the sigma function. It is entirely feasible to go through and take the derivative of this analytically and calculate it. It just so happens that this function has a nice property that to get its derivative, you just multiply it by 1 minus itself. So this is very straightforward to calculate. Another element that we've used is the rectified linear unit. Again, to figure out how to backpropagate this, we just write out the relation. B is equal to A if A is positive, otherwise it's 0. And piecewise, for each of those, we take the derivative. So dB dA is either 1 if A is positive or 0. And so with all of these little backpropagation steps and the ability to chain them together, we can calculate the effect of adjusting any given weight on the error for any given input. And so to train, then, we start with a fully connected network. We don't know what any of these weights should be, and so we assign them all random values. We create a completely arbitrary random neural network. We put in an input that we know the answer to. We know whether it's solid, vertical, diagonal, or horizontal, so we know what truth should be, and so we can calculate the error. Then we run it through, calculate the error, and using backpropagation, go through and adjust all of those weights a tiny bit in the right direction. And then we do that again with another input, and again with another input, for, if we can get away with it, many thousands or even millions of times. And eventually, all of those weights will gravitate, they'll roll down that many-dimensional valley to a nice low spot in the bottom, where it performs really well and does pretty close to truth on most of the images. If we're really lucky, it'll look like what we started with intuitively understandable receptive fields for those neurons and a relatively sparse representation, meaning that most of the weights are small or close to 0. And it doesn't always turn out that way, but what we are guaranteed is that it'll find a pretty good representation of the best that it can do adjusting those weights to get as close as possible to the right answer for all of the inputs. So what we've covered is just a very basic introduction to the principles behind neural networks. I haven't told you quite enough to be able to go out and build one of your own, but if you're feeling motivated to do so, I highly encourage it. Here are a few resources that you'll find useful. You'll want to go and learn about bias neurons. Dropout is a useful training tool. There are several resources available. Applications of machine learning have gotten a lot of traction in the last few years. There's a couple of big categories that have had wins. One is identifying pictures, the equivalent of finding cats on the internet. In order to predict what you're going to have for dinner, you set up a neural network. The inputs to this neural network are a bunch of items like the day of the week, the month of the year, whether or not your flatmate was in a late meeting, variables that might reasonably affect what you're going to have for dinner. Now, if you're new to neural networks, I highly recommend you take a minute and stop to watch the as a voting process. And so in the neural network that you set up, there's a complicated voting process, and all of the inputs like day of the week and month of the year go into it, and then you train it on your history of what you've had for dinner, and you learn how to predict what's going to be for dinner tonight. The trouble is that your network doesn't work very well. Despite carefully choosing your inputs and training it thoroughly, you still can't get much better than chance predictions on dinner. As is often the case with complicated machine learning problems, it's useful to take a step back and just look at the data. And when you do that, you notice a pattern. Your flatmate makes pizza, then sushi, then waffles, then pizza again in a cycle. It doesn't depend on the day of the week or anything else. It's in a regular cycle. So knowing this, we can make a new neural network. In our new one, the only inputs that matter are what we had for dinner yesterday. So if we know if we had pizza for dinner yesterday, it'll be sushi tonight, sushi yesterday, waffles tonight, and waffles yesterday, pizza tonight. It becomes a very simple voting process, and it's right all the time because your flatmate is incredibly consistent. Now, if you happen to be gone on a given night, let's say yesterday you were out, you don't know what was for dinner yesterday. You can still predict what's going to be for dinner tonight by thinking back 2 days ago. Think, what was for dinner then? So what would be predicted for you last night? And then you can use that prediction in turn to make a prediction for tonight. So we make use of not only 43, the wind's 13 miles an hour, there's going to be a 1/4 inch of rain, and the relative humidity is 83%. That's all a vector is. The reason that it's used a vector for statements like, it's Tuesday. In order to encode this kind of information, what we do is we make a list of all the possible to see a long vector. So we can make a one hot vector for our prediction for dinner tonight. We set everything equal to 0, and it becomes a useful shorthand for describing this neural network. In each of those input vectors to every element in the output vector becomes our yesterday's predictions tomorrow. And we can go back as far as we need to and see what was for dinner, and then just trace it forward and play out our menu over the last 2 weeks until we find out what's for dinner tonight. So this was a nice simple example that showed recurring the words Doug, Jane, Spot, saw, and a period. And the task of the neural network is to put these together in the right order to make a good children's book. So to do this, we replace our food vectors with our dictionary vectors. Here again, it's just a list of numbers representing each of the words. So for instance, if Doug was the most recent word that I saw, my new information vector would be all zeros except for a 1 in the Doug position. And we similarly can represent our predictions and our predictions from yesterday. Now, after training this neural network and teaching it what to do, we would expect to see certain patterns. For instance, anytime a name comes up, Jane, Doug, or Spot, we would expect that to vote heavily for the word saw or for a period, because those are the 2 words in our dictionary that can follow a name.
Similarly, if we had predicted a name on the previous time step, we would expect those to vote also for the word saw or for a period. And then by a similar method, anytime we come across the word saw or a period, we know that a name for. So in this form, in this formulation, we have a recurrent neural network. For simplicity, I'll take the vectors and the weights and collapse them down. And there's one more symbol we haven't talked about yet. This is a squashing function, and it just helps the network to behave. Coming out, vote of 0.5 to the y number, and where the same value, you can imagine if in the course of that processing, say something got voted by you can so you would use the information from further back, and it's subject to these types of mistakes. In order to overcome this, we take our recurrent neural network and we expand it, and we add some more pieces to it. The critical part that we add to the middle here is memory. We want to be able to remember what happened many time steps ago. So in order to explain how this works, I'll have to describe a few new symbols that we've introduced here. One is another squashing function, this one with a flat bottom. One is an X in a circle, and one is a cross in a circle. So the cross in a circle is element by element addition. The way it works is you start with two vectors of equal size, and you go down each one. You add the first element of one vector to the first element of another vector, and then the total goes into the first element of the output vector. So 3 plus 6 equals 9. Then you go to the next element. 4 plus 7 equals 11. And so your output vector is the same size of each of your input vectors. Just a list of numbers, same length, but it's the sum, element by element, of the two. And very closely related to this, you've probably guessed, the X in the circle is element by element multiplication, since 3, 8. Again, the output. Now, element-wise multiplication lets you do something pretty cool. You imagine that you have a signal, and it's like a bunch of pipes, and they have a certain amount of water trying to flow down them. In this case, we'll just assign the number to that of 0.8. It's like a signal. Now, on each of those pipes, we have a faucet, and we can open it all the way, and a closed faucet, we get right through and 0 and smaller. It's attenuated. What? Now, in order to do gating, it's nice to have a value that you know is always. This will. It's very 0 and 1. Now, when we introduce all of these together, what we get, we still have the combination of our previous predictions and our new information. Those vectors get passed, and we make predictions based on them. Those predictions get passed through, but the other thing that happens is a copy of those predictions is held onto for the next time step, the next pass through the network. And some of them, here's a gate right here, some of them are forgotten, some of them are remembered. The ones that are remembered are added back into the prediction. So now we have not just prediction, but predictions plus the memories that we've accumulated and that we haven't chosen to forget yet. Now there's an entirely separate neural network here that learns when to forget what. Based on what we're seeing right now, what do we want to remember? What do we want to forget? So you can see this is powerful. This will let us hold on to things for as long as we want. Now you've probably noticed though, when we are combining our predictions with our memories, we may not necessarily want to release all of those memories out as new predictions each time. So we want a little filter to keep our memories inside and let our predictions get out. And we add another gate for that to do selection. It has its own neural network, so its own voting process, so that our new information and our previous predictions can be used to vote on what all the gates should be, what should be kept internal, and what should be released as a prediction. We've also introduced another squashing function here. Since we do an addition here, it's possible that things could become greater than 1 or smaller than -1, so we just squash it to be careful, to make sure it never gets out of control. And now, when we bring in new predictions, we make a lot of possibilities, and then we collect those with memory over time. And the only other piece we need to add to complete our picture here is yet another set of gates. This lets us actually ignore possible possibilities as they come in. This is an attention mechanism. It lets things that aren't immediately relevant be set in only a gate you're ready of writing our children's book. And for the brain, so far is Jane's word. The names Doug, Jane, and Spot were all predicted as viable options. This makes sense. We had just wrapped up a sentence with a period. The new sentence can start with any name, so these are all great predictions. So we have our new information, which is the word Doug. We have our recent prediction, which is Doug, Jane, and Spot. And we pass these two vectors together to all 4 of our neural networks, which are learning to make predictions, to do ignoring, to do forgetting, and to do selection. So the first one of these makes some predictions. Given that the word Doug just occurred, this has learned that the word saw is a great guess to make for a next word. But it's also learned that having seen the word Doug, that it should not see the word Doug again very soon, seeing the word Doug at the beginning of a sentence. So it makes a positive prediction for saw and a negative prediction for Doug. It says, I do not expect to see Doug in the near future. So that's why Doug is in black. So this example is so simple we don't need to focus on attention or ignoring, so we'll skip over it for now. And this prediction of saw, not Doug, is passed forward. And again, for the purposes of simplicity, let's say there's no memory at the moment, so saw and Doug get passed forward, and then the selection mechanism here has learned that when the most recent word was a name, then what comes next is either going to be the word saw or a period. So it blocks any other names from coming out. So the fact that there's a vote for not Doug gets blocked here, and the word saw gets sent out as the prediction for the next time step. So we take a step forward in time now. The word saw is our most recent word and our most recent prediction. They get passed forward to all of these neural networks, and we get a new set of predictions. Because the word saw just occurred, we now predict that the words Doug, Jane, or Spot might come next. We'll pass over ignoring and attention in this example, and we'll take those predictions forward. Now, the other thing that happened is our previous set of possibilities, the word saw and not Doug, that we were maintaining internally, get passed to a forgetting gate. Now, the forgetting gate says, hey, my last word that occurred was the word saw. Based on my past experience, then I can forget about, I know that it occurred, I can forget that it happened, but I want to keep any predictions having to do with names. So it forgets saw, holds on to the vote for not Doug, and now at this element by element addition, we have a positive vote for Doug, a negative vote for Doug, and so they cancel each other out. So now we just have votes for Jane and Spot. Those get passed forward. Our selection gate, it knows that the word saw just occurred, and based on experience, a name will happen next. And so it passes through these predictions for names. And for the next time step then, we get predictions of only Jane and Spot, not Doug. This avoids the Doug saw Doug period type of error and the other errors that we saw. What this shows is that long short-term memory can look back 2, 3, many time steps and use that information to make good predictions about what's going to happen next. Now, to be fair to vanilla recurrent neural networks, they can actually look back several time steps as well, but not very many. LSTM can look back many time steps and has shown that successfully. This is really useful in some surprisingly practical applications. If I have text in one language and I want to translate it to text to another language, LSTMs work very well. Even though translation is not a word-to-word process, it's a phrase-to-phrase, or even in some cases a sentence-to-sentence process, LSTMs are able to represent those grammar structures that are specific to each language. And what it looks like is that they find the higher level idea and translate it from one mode of expression to another, just using the bits and pieces that we just walked through. Another thing that they do well is translating speech to text. Speech is just some signals that vary in time. It takes them and uses that then to predict what text, what word is being spoken, and it can use the history, the recent history of words, to make a better guess for what's going to come next. LSTMs are a great audio. Robotics is nothing more than an agent taking in information into sequence. This is it. This is lifted straight from the Wikipedia page. I won't step through it, but it's encouraging that something that looks so complex expressed mathematically actually makes a fairly straightforward picture and story. And if you'd like to dig into it more, I encourage you to go to the Wikipedia page. Also, there are a collection of really good tutorials and discussions, other ways of explaining LSTMs that you may find.
There. If you're standing in the back, there are plenty of seats. Please feel free to filter in. So take the opportunity to ask the hard questions about the stuff that I didn't cover. If you don't know anything about it, this talk is for you. You can be forgiven if the summary, in case you want to take a nap. Deep learning is not magic, but it's really a fighter jet can fly, but there are a whole lot of things that an owl can do, and arguably it's a much more complex thing. Although what the fighter jet does, it does really, really well. So deep learning is the fighter jet. Highly specialized, highly, like all neurons, it's got a big body in the middle, long tail, and some arms that branch off. Here's an artist's conception of a neural network or a bunch of neurons. Again, big body, long tails. You can see long tails, some of which branch, and the arms are pretty much invisible. And again, picture of some brain tissue. Here the neurons are small dots, and you can barely see any of the tails at all. This is just to give you a sense of how tightly these things are packed together and how many of them there are. Big numbers with lots of first pictures of a neuron. Santiago Ramon de Cajal found his was able, and the arms are called dendrites. We're going to draw a cartoon version of them. Or whiskers, and they look for electrical activity. They pick it up and send it to the body. The more dendrite activity there is, the more axonal activity there is. And if you get all of the dendrites really firing, then that axon is just as active as it could possibly be. In a very simplistic way, a neuron adds things up. These little nubs or buttons, they're actually called boutons on the dendrite. There's a little connection there. We'll represent that connection by a circle. And the diameter of that circle is the strength of that connection. Big circle, strong connection. And it can connect strongly or weakly or somewhere in between. The upstream neuron with a long link. That can be two. Now, this starts to get interesting because many different input neurons can connect to the dendrites of a single output neuron. And each connects to, and for that, substrate tissue. Here, this is done. Let's say you have 5 inputs, very live. So you have a really low temperature, and input neurons can connect to many outputs. We could have an eyeglasses example too. And taking a step back, we actually have some domain knowledge here. We know he's got 2 schedules. Working in the morning, off in the morning. Working in the morning, off in the evening. Here is a hard work creator, generator. Work. Similarly, we can take higher activity. That's the one we care about. How wrong is it? Well, if it was perfect, if our neural network was perfect, that would have an activity of 1. You make if you shift it a little bit to the left, we go. So our error went from, we call it deep. This is your first layer of outputs. They're common before, perhaps words in the English language, if that's short phrases, and so forth. And you can do this as deep as you like. Inputs pixels and show, instead of looking at shawarma guy schedule, you're looking at individual pictures as your training data set. These are the image of faces here, a third layer outputs. Here's an output of some of the output neurons of an 8-layer neural network. And as you get deeper, you can see things that are clearly recognizable and quite complex artists. So here's some research where output neurons were learned based on information about artists, and we get to the input. Turns out you can take Atari 2600 games, take the pixel representations, feed those in as input neurons, learn some fun features, and then pair it with something else called reinforcement learning that learns appropriate action. And it uses a pair of deep neural networks, one to interpret the video, one to learn to understand its own movements, and then pairs that with some other execution software to cook based on the video representations that it's seen. So while it's not magic, it's pretty cool. You can do something. You can think of a lot. So until they wave signs at me from the back, we have a couple. Oh, we're waving signs at the back. So we are done.
Discovery Houston, trim to ATO. Beautiful, beautiful.
Hello, welcome to How Convoluted Spots Dark Spots. That things pattern is powerful. Usually when we talk about them, we do so in the same way we might talk about magic. But they're not magic. What they do is based on some pretty basic ideas applied in a clever way. So to illustrate these, we'll talk about a very simple toy convolutional neural network. What this one does is takes in an image, a 2-dimensional array of pixels. You can think of it as a checkerboard, and each square on the checkerboard is either light or dark. And then by looking at that, the CNN decides whether it's a picture of an X or of an O. So for instance, on top there, we see an image with an X drawn in white pixels on a black background, and we would like to identify this as an X. And the O, we'd like to identify as an O. So how a CNN does this has several steps in it. What makes it tricky is that the X is not exactly the same every time. The X or the O can be shifted, it can be bigger or smaller, it can be rotated a little bit, thicker or thinner, and in every case we would still like to identify whether it's an X or an O. Now the reason that this is challenging is because for us, deciding whether these two things are similar is straightforward. We don't even have to think about it. For a computer, it's very hard. What a computer sees is this checkerboard, this 2-dimensional array, as a bunch of numbers, ones and minus ones. A 1 is a bright pixel, a minus 1 is a black pixel. And what it can do is go through pixel by pixel and compare whether they match or not. So to a computer, it looks like there are a lot of pixels that match, but some that don't. Quite a few that don't, actually. And so it might look at this and say, I'm really not sure whether these are the same. And so it would, because a computer is so literal, it would say, uncertain. I can't say that they're equal. Now, one of the tricks that convolutional neural networks use is to match parts of the image rather than the whole thing. So if you break it down into its smaller parts or features, then it becomes much more clear whether these two things are similar. So examples of these little features are little mini images. In this case, of the bigger image. The way this is done is a feature is lined up with the little patch of the image, and then one by one, the pixels are compared. They're multiplied by each other. To step through this to see why it makes sense to do this, you can see starting in the upper left-hand pixel in both the feature and the image patch, multiplying a 1 by a 1 gives you a 1. And we can keep track of that by putting that in the position of the pixel that we're comparing. We step to the next one. Minus 1 times minus 1 is also a 1. And we continue to step through pixel by pixel, multiplying them all by each other, and because they're always the same, the answer is always 1. When we're done, we take all these 1s and add them up and divide by 9, and the answer is 1. So now we want to keep track of where that feature was in the image, and we put a 1 there. Say, when we put the feature here, we get a match of 1. That is filtering. Now we can take that same feature and move it to another position and perform the filtering again. And we start with the same pattern. The first pixel matches, the second pixel matches. The third pixel does not match. Minus 1 times 1 equals minus 1. So we record that in our results. And we go through and do that through the rest of the image patch. And when we're done, we notice we have 2 minus 1s this time. So we add up all the pixels, which add up to 5, divide by 9, and we get a 0.55. So this is very different than our 1. And we can record the 0.55 in that position, where we were, where it occurred. So by moving our filter around to different places in the image, we actually find different values for our possible position. We do convolution. That's just the repeated application of this feature, this filter, over and over again. And what we get is a nice map across the whole image of where this feature occurs. And if we look at it, it makes sense. This feature is a diagonal line slanting downward, left to right, which matches the downward, left to right diagonal of the x. So if we look at our filtered image, we see that all of the high numbers, 1s and 0.77s, are all right along that diagonal. That's where two other features. We can repeat that with our x filter in the middle and with our upward slanting diagonal line in the bottom. And in each case, the map that we get of where that feature occurs is consistent with what we would expect based on a bunch of we'll call a convolution filtered image. So convolution layer is one trick that we have. The next step, 2 pixels, just in window filter maximum value is 1. 2 pixels point. We have what's with so that's it with a smaller set of filtered images. Now, that's our second trick. Third trick, normalization. This is just a step to keep the math from blowing out here. Value, relational unit, negative value, change time negative value. And this becomes another type of layer. What's really fun, the magic starts to happen here when we take these layers, convolution layers, that each and by each and 1 slice of cheese and 1 lettuce and 1 tomato, but a whole bunch of layers, double, triple, quadruple deckers, as many times as you want. Each time the image gets more filtered as we pull layer in our toolbox. Now into one of our answers that we're going to vote for. Valid or contrary have weight and scan to list of feature categorize this input as an X. Cool, you have units. Then for so there are some things that we have glossed over here. You might be asking yourself in air, those waved my hand behind back propagation is that the error in the final answer is used to determine how much the network adjusts and changes. So in this case, if we knew we were putting in an X and we got a 0.92 vote for an X, and that would be an error of 0.08, and we got a 0.51 vote for an O, we know that that would be an error of 0.49, actually an error of 0.51 because it should be 0. Then if we add all that up, we get an error of what should be 0.59. So what happens with this error signal is another bit of something that to feature all amount that they're adjusting on a down. You find that doing that many times over lots of iterations, lots of steps, helps all of these values across minimum well parameters. These are not features choosing are in fact this type of layer. And in my new these we've been talking about images, but you can use what's more. What I mean by that is if you look at an image, 2 rows of pixels or 2 columns of pixels are right next to each other, they're more closely related than rows or columns that are far away. Now what you can do is you can take something like sound and you can chop it up into little time steps, and for each piece of time, the time step right before it and right after is more closely related than time steps that are far away, and the order matters. You can also chop it up into different frequency bands, bass, mid-range, and you can do something similar with text, where the position in the sentence becomes the column and the row is words in a dictionary. Matter close to networks is that they're really designed to capture local spatial patterns. Spatial in the sense of I have each row is a separate customer, each column is a separate piece of information about that customer, such as their name, their address, what they bought, what websites they visited. Then this doesn't so much look like a picture. I can take and rearrange those columns and rearrange those rows, and this still means the same thing. It's still equally easy to call possible. So as a rule of thumb, if your data is just as useful after swapping out any of the columns for each other, is that convolutional neural networks are great if you'd like to stand for checking out the writings of Christopher Olah. He's an exceptionally clear writer. And feel free to check out another presentation that I did, Deep Learning Demystified.